So there's a couple key situations in which we want to be very comfortable talking about the electric potential energy and how it changes. And the simplest of those is to talk about the electric potential energy within a constant electric field. And so again, the analogy that we want to sort of use here is bringing ourselves back to what we know about the constant gravitational field near the Earth's surface. So if we think about for an object near the Earth's gravitational field, the gravitational force is pulling down on that object. So if the object moves up, then the work done by the gravitational force is negative because the displacement points in the opposite direction as the force. And again, you, in moving that object upwards, you did work against the gravitational force, which increased the gravitational potential energy. If, on the other hand, let's say you let that object go and it falls back down, well, now under this situation, the gravitational force is doing positive work, so the work done by the gravitational force is positive, and the gravitational potential energy is decreasing. And of course, the interesting detail to keep in mind here is that the gravitational force points down because the gravitational field points down, and mass is always a positive scalar quantity, so the gravitational force and the gravitational field always point in the same directions. So if we think about what's going on for an object in a constant electric field, well, one of the things that we need to do now is we need to talk about what type of charge do we have. So unlike mass, where we only have positive mass, we can have both positive and negative charge. So let's start by talking about if our charge is positive. So we placed a positive charge in a constant electric field. So because the charge is positive, I know that the electric force and the electric field are going to point in the same direction. So the force acting on the charge points in the same direction as the electric field. So if I let that charge move with the electric field, then the electric force is doing positive work and the electric potential energy has to decrease as a result of that. On the other hand, if I move the charge against the electric field, now the electric force is doing negative work, right? The object is being moved by some external agent, probably me. So I'm moving this charge against the electric force. So I'm doing positive work on it. The electric force is doing negative work on it. And that means that the electric potential energy is increasing. So the positive work that I do goes into increasing the electric potential energy of the charge. Well, what about if the charge is negative? Well, for starters, I know if the charge is negative, then the electric force acting on the charge points in the opposite direction as the electric field. And so now if I think about moving with the electric field, so the electric force points to the left in this picture, but my charge is moving to the right. So this is a situation where the force and the displacement point in opposite directions, which means the work done by the electric force is negative, and therefore the electric potential energy has to increase. So I had to do work to move that charge against the electric force. The work I did, the positive work I did, went into increasing the electric potential energy of the charge. On the other hand, if a negative charge moves against the electric field, well, in this case, for a negative charge moving against the electric field, that means it's moving with the electric force. And by moving with the electric force, that means the electric force does positive work, so the electric potential energy decreases. So if you give objects the chance, so if you let objects go, they'll always work to lower their potential energy if they can. So again, if I let a mass go within a gravitational field, it's going to fall in the direction of the gravitational field to lower its gravitational potential energy. On the other hand, if I release a charge in an electric field, it will also move to lower its electrical potential energy, but which way it moves relative to the electric field now depends on which type of charge you have. So do I have a positive charge or do I have a negative charge? Let's sort of derive an equation here for how we can calculate the change in the electric potential energy in a constant electric field. So let's say I've got a positive charge. That way I know that the electric force and the electric field are going to point in the same direction. Let's assume that I move that charge in the direction of the electric field. So in this case, the electric field points to the right. I'm letting that be the positive direction here. I know that what the electric force wants the charge to do is it wants it to move. So if you let the charge go, the electric force is going to pull the charge to the right. It wants to pull my positive charge in the direction of the electric field. So if I think about the equation that we use to define the change in the electric potential energy, right, that's negative, an integral from an initial position to some final position. of the dot product of the electric force with my tiny little infinitesimal displacements in position. And so I can do a couple of things. One is I need to deal with this dot product. And so for starters, because the electric force and my infinitesimal little displacements as I move in the direction of the electric field, those point in the same direction. So that means this is going to be a positive quantity. I can get rid of the dot product there. I can also plug in QE for the magnitude of the electric force. So this is just saying the electric force acting on my charge is going to be equal to the amount of that charge times the strength of the electric field. So I'm left with this expression to integrate from some initial position in x to some final position in x of QE dx. Well, since my charge doesn't change and it's a constant electric field, both Q and E I can pull out of the integral, and I'm left with the integral from some initial x to some final x of dx, which just ends up giving me delta x. So the thing to keep in mind is that this delta x is defined to be in the direction of the electric field. Okay? So it's a displacement that is parallel to E as a vector field. It's also been defined to be positive if you're moving in the direction of the electric field and negative if you're moving in the opposite direction of the electric field. So if you think about what we've got here, so here's my negative sign out front. If I have a positive charge, the electric field strength is a positive quantity. And if my charge moves in the direction of the electric field, then I'm going to have negative, positive, positive, positive. This tells me that the quantity that I've just calculated here will be negative, which tells me that the electric potential energy decreases. On the other hand, if I move my charge, instead of moving it to the right in the direction of the field, I move my positive charge in the opposite direction. So again, in this case, that would mean moving it against the electric force. So I know that I'm going to increase the electric potential energy if I do that. Well, again, I've got a negative sign sitting out front, positive Q, positive E, but now my displacement is negative because it's moving opposite the direction of the electric field. That negative in my displacement is going to cancel the negative out front, and sure enough, I get an increase in the electric potential energy. So this equation has been set up, but there's a couple special ways that we've defined delta x here that we just need to pay attention to. It's along the field, and it's positive if it's in the direction of E, it's negative if it's opposite the direction of E. So if I want to think about using my equation to figure out whether or not the electric potential energy is increasing or decreasing, well, I can see from this that the electric potential energy is going to increase when I have a charge moving in a constant electric field. If it's a positive charge, so Q is positive, then for my delta U to be positive, I need delta X to be negative to cancel out that negative sign. So when my positive charge moves against the electric field, I end up with an increase in the electric potential energy. On the other hand, if Q is negative, then Q will cancel out the negative sign, and I need delta X to be positive. So a negative charge moving with the electric field also increases the electric potential energy. On the other hand, if I want to decrease the electric potential energy, if I have a positive charge, I want to decrease, so I need that negative sign out front. Q is always positive. I need delta X to be positive, so a positive charge moving with the electric field decreases the potential energy. A negative charge, on the other hand, I need delta X to also be positive so that I basically have three negatives over here and still end up with something that's negative to have a decrease in the electric potential energy. So a negative charge moving against the electric field decreases the electric potential energy. Now another way that we can reframe this, because again we're sort of embedding something vector-ish by thinking about this component as a component that can be positive or negative. So our other option here is that we can sort of reframe this equation, make it an entirely scalar thing, and now we're responsible for the sign out front. So we're always going to use a positive charge. We're going to do the absolute value of the charge. The electric field strength is always positive, and we're going to define this distance. So this is also going to be positive. So this is the distance we've moved parallel to the electric field. So in this case, this distance doesn't care whether you're moving with the field or against it. It's simply interested in that distance. We take care of the sign out front. So if you have a positive charge, we want to make sure that we end up with a positive if we move opposite the direction of the electric field, a negative if we move in the direction of the electric field. So we can either keep track of the signs of delta X and let this equation take care of it, or we can basically think about what's going on and whether the potential energy is increasing or decreasing. We take care of the sign out front and then multiply together three positive quantities. Now notice that this parallel distance, so d parallel, it's still only interested in the parallel distance. So it doesn't matter whether your displacement also has some component that's perpendicular to the electric field. That component never counts. It's only ever interested in the distance you move parallel to the electric field. So if we want to talk about the electric potential energy, well, as we've talked about with any potential energy, to talk about the electric potential energy, we need to have a 0 point. And so in this case, in a constant electric field, just like we did with a constant gravitational field, the 0 point is really arbitrary. And so we can pick wherever we want the 0 point to be. So if I put the 0 point for electric potential energy where the charge is initially located, then now I need to think about whether or not I need a positive or negative sign if I think about the electric potential energy of that charge as I move it away from that 0 point, is basically like thinking about, well, have I moved it above or below in terms of our gravitational analog? So above the 0 point means, again, you move the charge against the electric force. So that's the way we know that we increase the electric potential energy. So if you start at the 0 point and move your charge with or against the electric force, then you clearly have increased the electric potential energy. It was 0, now it has to be positive. If, on the other hand, you move your charge with the force, then you've moved below the 0 point. So moving with the force, the electric force, means that you've decreased the potential energy. So if you're below the 0 point, then we're going to use our negative sign out in front.